Happy Monday, guys, and welcome to another episode of Physical Science at Home. So today we're going to be starting a new unit. This unit is Unit 10, makes sense, comes after Unit 9. And as you'll see on the screen here, it's all about energy. So we're going to be talking about energy today. My hope is that this unit will be a little bit easier than the past couple of units. I know the unit on force is pretty tough. Hopefully the unit on motion was pretty easy. I'm hoping that this next unit on energy is about as difficult as the motion unit. That's the hope. Best thing you guys can do to make it easy for yourself is to follow along with a notebook and some paper and kind of jot down today. A lot of it's going to be definitions. So jot down kind of the important definitions, the important facts for today. So let's get into notes. 10.1 energy definitions. We're going to start with the definition of energy. And the definition for energy is the ability to do work. So you're going to want to write that down, that definition down for energy. Now, unfortunately, this word work has a very specific meaning in the world of science. So we're going to have to define work. And the definition for work, go ahead and write this down. Work is the application of a force over a distance. Now, those words force and distance also have very specific definitions to them. So, work is the application of a force over a distance, but force, remember from a couple units ago, a force is a push or a pull. So, when I saw these three definitions, I figured, Mr. Smith, there's got to be a way to kind of put all these together so that each one of them makes sense without having to look at every one of them. So I'm going to use a little math here, do a little substitution. If you guys have ever done that before, where you have two different equations and you substitute one in the other to kind of figure out an answer to a two-equation math problem. So here's what we're going to do. You ready? Energy is the ability to apply a push or a pull over a distance. So energy is the ability to do work. Work is the application of a force, and a force is a push or a pull, right? So energy is the ability to apply a force, apply a push or a pull over a distance. Now, after writing that definition down, that's a lot of words. Energy is the ability to apply a push or a pull over a distance. So what I thought would be helpful is to look at some different examples, because right now this kind of all seems very similar, all seems the same, and that's not okay. We want these definitions to look different. We want these terms to be distinct to you guys. So let's take a look here at the next slide. A force is a push or a pull. So an example of a push or a pull would be something like lifting a 50-kilogram box. If you were to lift a 50-kilogram box, you would be applying a force to that box. Now remember, work here is the application of a push or a pull over a distance. So in work, you wouldn't be lifting the 50-kilogram box. That's a force. In work, you would have to lift a 50-kilogram box up 2 meters in the air. So that right there is work. It's a push or a pull, and it's a distance combined. So work has the fact that you're lifting the box and that it's going 2 meters in the air. And then you'll see at the end there, I wrote down takes 980 joules of work. You'll figure out later, I think actually tomorrow, we'll talk about how to calculate work and how we get that number, how we get that J, which stands for joules. So we'll talk later about all that and kind of where that comes from. Now, energy is the ability to apply a push or a pull over a distance. Energy and work are very, very similar. Here's the example I came up with relating the box to lifting it up in the air. Energy would be if you lift that 50-kilogram box 2 meters up in the air, the box now is going to have 980 joules of energy. So the difference here between work and energy is when you're lifting the box, you take 980 joules of work. The person lifting the box uses or does that work. Now, the fact that the box went from being on the ground to now up in the air, it now has something we will call potential energy. And so now the box has that 980 joules of work that's transferred to the box. So now this box has an extra 980 joules of what we call energy. Hopefully that makes sense. Work is something that a person is applying to a box, and now the fact that the box is higher up, it has energy. We're going to talk more about energy, but for now, I hope you're feeling more comfortable with force, work, and energy. And if not, stay tuned, because these aren't going to go away. We're going to continue to look at the differences between them. Does that sound good? Hopefully it does. So, once again, lifting a 50 kilogram box is the example. Now what we're going to say is that lifting a box, that's the same thing as a force. Hopefully that makes sense. Work is going to be lifting the box a specific distance. In fact, later we're going to talk about a formula for work. And work is mass times distance. Force times distance. So you'd have to figure out how much force is a 50 kilogram box. You can do that by finding its weight, and then you can figure out the distance, multiply those two together, and you've got work. Now, energy is saying that the box has energy because the box is a specific distance above the ground. So work, we had to lift the box, but now the box just has energy because it's above ground. And remember, that's called potential energy. Great. So earlier I talked about a potential energy, or I just did. There's 4 different classifications of energy. We've got chemical, nuclear, and electromagnetic. Those are 3 of them. We're not going to focus on these type of energies. If you were to become a nuclear physicist or a nuclear chemist, you would need to know nuclear, and if you were to become a chemist, you'd need to know chemical, and if you were to become a full-on physicist, you need to know more about electromagnetic. But energy is kind of complicated enough as it is that we're just going to talk about mechanical energy. So when we talk about mechanical energy, there's 2 types of mechanical energy. Type number 1 is potential energy. Go ahead and write this down. Potential energy is energy stored based on an object's mass and position. So 2 things here we're noticing, mass and position, that's going to dictate energy. Kinetic energy is going to be energy stored based on an object's mass and speed. So you'll notice that the potential and kinetic energy definitions are very, very similar. They're both looking at energy stored, and it's based on mass for both of them. But then for potential, we're looking at position. For kinetic, we're looking at speed. Hopefully you've heard the word kinetic referring to motion before. And then potential, position. Those kind of, they have the same letter. So that's nice. That's an easy way to remember it. Potential is all about position, height, distance, that sort of thing. The last type of energy we're going to talk about is thermal energy. So when you think thermal energy, I want you to think of this word right here, friction. Thermal energy is energy lost due to friction as an object moves. So anytime we're moving in the real world, there's going to be friction produced. A lot of times though, for the purposes of our class, we're going to ignore this thermal energy and we're just going to focus on the difference between potential and kinetic. So we'll call potential and kinetic scenarios where we're only working with those 2, we'll call those basic. And then if we incorporate any thermal energy, we'll talk about those as complex systems. Sound good? So make sure you have a definition for potential, kinetic, and thermal energy, and then let's move on to the next slide. Great, so it says we'll only focus on mechanical energy this unit. That's awesome. In an ideal setting, basic, ideal, same thing, we're talking about potential energy and kinetic energy. Hey, just be aware, we abbreviate potential energy as PE, and we abbreviate kinetic energy as KE. In an actual setting then, thermal energy is abbreviated TME, thermal energy. Sound good? have those abbreviations down in your notes. Oh, other thing here. Energy is measured in this unit J, which is pronounced joules. You can laugh at that if you'd like. Fun fact, a joule, a J, is equal to a kilogram times a meter squared divided by seconds squared. Why I showed you that is just because when we look at equations, potential energy and kinetic energy have very different equations, but they both end up incorporating kilograms, which is a unit for mass, meters, and seconds. So maybe they'll look at speed, which is meters divided by seconds. Maybe they'll look at time versus position. A bunch of different ways you can get these units, but know that potential, kinetic, and thermal all work with the unit for energy, which is joules, J. And that's the same energy for work, or the same unit for work is joules as well. Okay, so have down joules, have down those abbreviations for potential, kinetic, and thermal, and let's move on to the next slide. Law of conservation of energy. Great. So first thing I want you guys to know here is that energy is never created, nor is it ever destroyed. Now, this is tough because in our world, it looks like energy gets created and it looks like energy gets destroyed. What's really happening here is not that we're creating or destroying energy, but we might say that we lose energy. When we're talking about that, what we're really saying is energy is changing forms. So I've got 3 examples for you. Number 1 is a skier slides down a hill. That's one example where energy is changing forms. So you might think that as the skier is sliding down the hill, it's gaining energy. But really, that's not how it works. We'll talk about that. Same thing with a ball rolling up a hill and stopping at the top. You might think that as that ball rolls, it's losing energy. That's not how it works. Or a ball rolls across a flat surface and eventually stops. You might be thinking as that ball's rolling, it's losing energy. Again, that's not how it works. In all 3 of these situations, energy is just changing forms. So let's take a look at it. There are 3 types of conversions. Let's focus on the first 2. For the first one, we have converting potential energy into kinetic energy. Then the second example we have is kinetic energy converting into potential energy. So you see how those are kind of related, and they play into the 2 scenarios we talked about at the start. A skier sliding down the hill is an example of potential energy being converted into kinetic energy. So at the top of the hill, the skier is at a high position. It has what we call a high potential energy. As the skier slides down the hill, it's going lower, but it's also increasing its speed. So now what we're seeing here is we're seeing our potential energy decrease and our kinetic energy increase. But as they change, the total amount of energy stays the same. And I'll show that to you in the next slide in a little bit. The ball rolling up a hill and stopping at the top is kinetic energy getting converted into potential energy. As the ball's rolling up, it's increasing its position, so its potential energy is increasing, and it's also slowing down. Its kinetic energy is decreasing. But if it starts here, they're going to end up with the exact same amount of energy. Now, in both these scenarios, you might not get a 100% conversion, so all of your potential energy might not all convert into kinetic energy, and that has to do with a kinetic energy conversion into a thermal energy conversion. So this is what we see actually in the real world, is that always our kinetic energy, some of it is being converted into thermal energy. This can be an example like if you spin a tire, your tire's moving, and as it's spinning on the ground, on the asphalt, that tire's going to heat up, right? You might burn some rubber or something like that. This is also why a soccer ball, if you kick it across the grass, it's going to slow down. It's going to slow down due to friction. And as that soccer ball slows down, just like the tire spinning on the asphalt, it's going to heat up. Now, the difference between the tire heating up on the asphalt and the soccer ball heating up as it moves across a field, there's not the soccer ball doesn't like catch on fire. It doesn't burn the grass, right? But it will heat up a little bit. A lot of that heat will just be lost to like all the blades of grass maybe the water on the grass, maybe the air. But there is thermal energy being created as a soccer ball slows down. Hopefully that helps. Hopefully that makes sense. Um, the kinetic to thermal energy conversion is less important to me than potential energy and kinetic energy, those changes. So what I'd like to do is I'd like to show you a clip here. Oh, and fun fact, if you want to read what happens to a baseball thrown at 90% the speed of light, there's a little link on the PowerPoint that you guys have access to. So take a look at that. It's really cool, really fun. Has to do with thermal energy and kinetic energy. I think it's cool. Okay, so let's look at our conservation of energy. Let's look at it a little bit as an example. So once again, energy can't be created, can't be destroyed, and the total energy in a system never changes. So let's look at a basic system here. We've got a ball, it's on a hill, and you'll notice that because it's high on the hill and it's stopped, all of its energy right now is potential energy. None of its energy is kinetic energy. I think there are 3, 4, 5, 6, 7, 8. There are 8 little segments here. So we'll say that right now we have a total energy of just 8 joules from the ball being on the hill, and it's all potential. What I want you to notice is what happens as this ball rolls down the hill. There's the ball rolling down the hill. Let me show you that one more time. Hopefully what you noticed is that as the ball is rolling down the hill, all of our potential energy slowly gets converted into kinetic energy. If you pause this video at the halfway point of the conversion, you'll notice that it's halfway down the hill and the kinetic versus potential energy is about the same, which should make sense, right? As it's rolling down, it's slowly gaining more kinetic energy, and as it's rolling down, it's losing potential energy because it's at a lower position now. So that is a basic system where the only 2 things we're looking at is potential and kinetic. Let's go ahead and look at a more complex system. In a more complex system, now we're also going to have thermal energy. So hopefully you'll be able to see a difference in the speed of the ball as it rolls down the hill. That's if I did this animation right. We'll see. Here we go. So hopefully you notice now that as the ball is rolling down the hill, it kind of started to slow down at the end. I don't have a great way to make this exactly what's supposed to happen, but the ball should be kind of slowing down more consistently as it's moving. You'll also notice then that because its final speed isn't as high as it was in the previous example, that we have more thermal energy here. So some of this kinetic energy gets converted into thermal energy, but again, you'll notice we've got 2 squares filled with thermal energy, 6 squares filled with kinetic energy. That's a total of 8. Remember, we started with 8 squares filled with potential energy. So energy is still conserved in this system, even though all of our potential energy doesn't all convert into kinetic energy. There it is once again. Okay, so that's the end of the notes for today. Let's quick flip back to the very beginning here. Alrighty then. So the definitions we want you to know, energy, work, and force. I think that I like the definitions on the second slide where I kind of plug in the previous definition from each one. So work is the application of a push or a pull over a distance, and energy is the ability to apply a push or pull over a distance. I think those definitions are nicer because they get more into the heart of what energy, work, and force are. Other definitions to know. Please know potential energy and kinetic energy. Potential is all about position, how high something is. Kinetic energy is all about speed, and they both have to do with mass. And then also know thermal energy. That's energy. We're talking about friction here. Know the abbreviations for potential kinetic energy, and know that energy is measured in joules. I would have it written down kilograms times meters per second divided by second squared. Know that that's a joule just because when it comes to equations tomorrow, we'll really look at that a lot. Know that energy is conserved always and that it just changes forms. And feel comfortable with how the energy is being converted from kinetic to potential as a ball rolls down the hill. Okay, that's the end of notes. I know it was a little long today, so thank you for paying attention. I hope you have a great rest of your day and take care. Bye-bye.